Okay, so we're going to do a quick video on some net ionic reactions. So this picture right here is, you can see that we have two aqueous solutions, and as the one aqueous solution hits the other aqueous solution, you can see there's kind of like a reddish brown glob forming, and that's a precipitate. It's an insoluble product that's being formed. So, and what net ionics do is they address like how do we appropriately kind of express these or write them. So we can write a normal reaction, but is that really the best way? Okay, so net ionic reactions, basically a lot of reactions take place in water, and when we typically write like a double replacement, which is the most common for net ionics, is we write this, and that's perfectly fine. However, what it doesn't really take into account is when ionic compounds are in water, most of them dissociate, and when we say dissociate, it just means they break into their cations and anions. So when you have salt water, so for example sodium chloride, when you put it in water, it becomes an Na plus 1 and it becomes a Cl minus 1. So you don't really have salt anymore, you actually have these ions floating around. So what we can do is you can do what's called a complete ionic equation, and what it does is anything that's aqueous is going to break apart for honors chem. If you take AP Chem or in college, you'll learn more stuff. But you can see that AgNO3 is aqueous, so you can see I broke it apart into the Ag plus 1 and the NO3 minus 1. And NaCl is aqueous, so I have Na plus 1 and Cl minus 1. That should say aqueous. That's just my fault there. AgCl as a product is a solid, so we don't break that apart. If it's a solid, a liquid, or a gas, it doesn't break. So we just let it there. And then NaNO3 is aqueous, so you can see we get Na plus 1, which is aqueous, and NO3 minus 1, which is aqueous. That's a complete ionic. What you can see on both sides is there's a couple ions that are exactly the same. So you can see we have Na plus 1 and we have Na plus 1. And what they are called is they're called spectator ions because they just spectate. They're not actually involved in the reaction. They're just there where it's happening. So we typically cross them out. Let me see if I can, oh, never mind, there we go. And they actually disappear. So you can see that the NO3 gets crossed out, the Na gets crossed out. Now, Ag plus 1 stays and Cl minus 1 stays because they're inherently different on the other side. We formed a solid, so they actually changed what they were doing. And then what's left over is called your net ionic reaction. So you can see we have the Ag plus 1, the Cl minus 1, which again should have the AQ, and then the AgCl, which is a solid. So the net ionic equation shows only the particles that are directly involved in the reaction. We don't show anything that was just around it. We only show the stuff that's directly there. All right, so we're going to do a couple practice problems. So the first thing we want to do, we want to write the net ionic equation and identify any spectator ions. So these two things form. So first thing we have is potassium hydroxide, which is KOH. And again, you can check your charges. Second thing is iron 3 chloride, which looks like this. It's a double replacement reaction. They say that we get a precipitate of iron 3 hydroxide. So it looks like this. And we have to figure out our other thing. And our other thing would be KCl. Oh wait, the iron hydroxide should be a solid. That's my fault. And we have this. So what we have here is that we just have to balance it. So we would need 3 KOHs and 3 KCls. So that's the reaction. Next thing you do is you do your complete ionic one. So what we have here is we have 3, oops, I don't want to be in subscript form. So 3 K plus 1s. Oh, well. Okay, sorry about that. I had to stop for a second. Someone needed me. So we're back here for part 2, if it likes me. Okay, so what we do is we break it apart. So we have 3 potassium ions. We also would have 3 hydroxide ions. It helps if my computer cooperates. The iron chloride is also aqueous, so that breaks apart. So we have an iron that's plus 3. And then there's Cl3. When that becomes ionized, it becomes 3Cl minus 1. So they break apart, and it's an aqueous. On the other side here, the iron hydroxide does not break apart. So we have the FeOH3 solid staying. And then our last thing is aqueous, so that breaks apart. So we have 3 potassium ions, which are aqueous, and 3 Cl minus ones, which are aqueous. So this would be called your complete ionic, and you would have to, let's see if it likes me. Doesn't like me. Okay, so you would have to, anyways, cross out things. So what you would do is the ones that are exactly the same, you would get rid of. So on this side, there's 3K plus 1s, and there's 3K plus 1s. So you would cross those out. For some reason, my pen's not working, so I can't do it. But cross out the Ks. And then if you look here, we have 3 Cl minuses and 3 Cl minuses. So those are exactly the same. So cross those out. So what your net ionic would look like is your Ks go, your Cl's go, and you're left with 3 hydroxide ions with with an iron plus 3 ion, and it gives you your solid here. And then your spectator ions would be your potassium ion and your chloride ion. So what you should do is pause the video, try the other practice problem on your own, and then I'm going to just put up the correct answer. So if you want to see it. Okay, here we go. When you're doing this one, what you should see is that on the other side, one of the things you make is HOH. You can leave it as HOH, or you can notice that HOH looks a lot like H2O, which is what it really is. And you should all know inherently that H2O is a liquid, not aqueous or anything. I mean, it is the liquid. Go back and balance, and we have 2 NaOHs and 2 waters. And hopefully that's the last interruption. I apologize. But anyways, you have your equation balanced, if it likes me. And you would break it apart. So we would have 2 hydrogen ions, which are aqueous, plus a sulfate ion. Ooh, that is not correct. I apologize. Which is aqueous. 2 sodium ions, which are aqueous, 2 hydroxide ions, which are also aqueous. Again, the water doesn't break, and then on this side we should have 2 sodium ions. I'm cheating, I'm just copying and pasting. We have a sulfate ion. And then your 2 waters don't change. I am struggling with typing here. I apologize. Alright, so you're all done. And then what you would do for your net ionic is you cross out anything that's exactly the same. So what that looks like down here is your your sulfate goes, your sodium goes, and you should have 2 hydrogen ions plus 2 hydroxide ions gives you 2 waters. And then spectators would be your sodium and sulfate ions. So hopefully this helps. If not, make sure you come in and get some help or read your book, or you're always welcome to look other things online. Tomorrow we're going to look at how can you tell if something is actually soluble or not, and then just a little tiny bit on oxidation reduction reactions.